Hey, everybody. It's Wednesday, April 21st. And as you can see here in the aim today, our goal for today's video is to review the two free response questions that were assigned for classwork yesterday. Now, everybody should have seen these problems in the same order on AP Classroom, and so I'm just going to go through them in that order. And so we'll start with number one. This problem here showed a figure at the top with a spring shown with no objects attached to it at what they called its relaxed length. And then they showed in figure 2 a cart held against a plate. And the problem said students intend to use a cart spring system to study motion. A vertical plate with negligible mass is attached to a horizontal spring of spring constant K. When the spring is at its relaxed length, the plate is at position D as indicated in the figure above. A cart is glued to the plate. The cart is initially held so that the spring is compressed as shown in figure 2 above. The maximum force the glue can exert is F max. Assume friction is negligible. The question goes on to say, the students plan to release the cart from rest so that the cart oscillates. They discuss whether the cart can detach from the plate during the cart's motion if the glue is not strong enough. One student makes the following claim. The cart can never detach from the plate because the cart and the plate always exert equal and opposite forces on each other, so the forces on the cart add to zero. Part A of this question says, which underlined phrases are correct, if either? If neither phrase is correct, write none. Now, what I'm about to show for my answer is an answer and an explanation, but I think it is really important, specifically for time management purposes, to pay attention to the exact structure of the question. It's really important to notice for this question in particular that there is nothing about this question that asks you to explain, which literally means they just want you to say which phrase is correct, and that's it. Now, obviously, because we're trying to understand these things, I'm going to talk about the explanation, but don't be surprised in the scoring guide when you see literally nothing about the explanation. So what I wrote here is the underlined phrase that's correct is the first phrase, the cart and the plate exert equal and opposite forces on each other. According to Newton's third law, whenever objects are interacting with each other, they always exert equal and opposite forces on each other. That's it. Period, end of story. This is a Newton's third law thing. Take a second to pause this video here and write that down if you want, and when you hit play, we'll take a look at the scoring guide. All right, so moving on to the scoring guide here, notice it's only 1 point, and that's because you just had to say which statement is correct. And so notice the scoring guide just says 1 point for a correct statement and no incorrect statements. And so really you could have just said the first statement, or the student is correct in saying that the cart and the plate exert equal and opposite forces on each other. That's the deal. Take a second to pause this video here and make sure you understand this part of the scoring guide. And when you hit play, we'll move on to part B. All right, part B of this question here, which I just included at the very bottom, says, which underlined phrase or phrases are incorrect if either? And if neither phrase is incorrect, write none. Remember, this person said, the cart could never detach from the plate because the cart and the plate exert equal and opposite forces on each other, which, notice, we already said was true. And then they go on to say, so the forces on the cart add to zero. Now, whether or not you remember this, this is something we talked about quite a bit when we were going over the dynamics unit. It's really important to realize when we say every action has an equal and opposite reaction as a way of stating Newton's third law, that way of stating it is a little sketchy because it really sort of misses the detail that what Newton's third law really means is that when object A exerts a force on object B, then object B exerts that force back on object A. That's the key distinction here. And so looking at the answer I wrote here, I wrote the underlined phrase that's incorrect is the second phrase. The forces on the cart add to zero. That's wrong. When Newton's third law says the cart and the plate exert equal and opposite forces on each other, that means the force on the cart is equal and opposite to the force on the plate. Forces can only cancel out if they act on the same objects. And the Newton third law action-reaction pairs always act on different objects, A on B, B on A. And there's no possible way that forces not acting on the same object can cancel each other out. That's a very, very important point, specifically because it's a big misconception in physics. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Looking at the scoring guide here for part B, Notice they're just looking for the answer. 1 point for an incorrect statement and no correct statements, basically just meaning you highlighted the correct part of what that kid said. And that could include the student is incorrect in saying the forces should add to 0, or simply by saying the second statement. Notice we've seen a pattern here now with this first and second statement business. I will say, I think it's important to point out this thing that you've been noticing now maybe in this pattern, that they keep using phrases like the first statement and the second statement in the scoring guide. These are both questions that appeared on versions of last year's AP exam, which was a modified version of the AP exam because 2020 AP exams were different. There were only 2 free response questions for physics. They were worth a different amount of points, scored differently, whatever. I would keep that in mind going forward. You particularly want to look for these questions if they ask you not only to point out the statement and then explain it. Keep that in mind. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to part C. Now I like this question, part C. We are slowly but surely working toward a simple harmonic motion test as we work through the homeworks and really get prepared for this thing. And I decided to assign this question because I think it does have a nice little simple harmonic motion part of this. And so it says here, the cart is removed and the plate is coated with a very strong glue. The cart rolls to the right with positive velocity v cart, collides with and sticks to the plate, and then oscillates back and forth at the end of the spring. The graph above shows the velocity of the cart as a function of time after it has completed several oscillations. Part C of this question here is asking you explain how this graph could be used to find the maximum compression of the spring as it oscillates. Now, if I'm honest here, I was a little unsure about how to answer this question when I first looked at it, because the first thing that popped into my mind was, well, it kind of depends on what we know, right? Because if you look at the initial description of the problem here, they say the vertical plate with the negligible mass is attached to the horizontal spring of a spring constant K. And they tell us there's a cart, but they don't exactly tell us what the mass of the cart is. And then if you look through in this part, notice they say nothing about the mass of the cart, whether or not you actually know that. And even in this second part here, they say the cart rolls to the right and has a velocity v cart, so they're kind of making it seem like you know that, but then they don't go on to say. So what I wrote here first was a little weird. I said if the cart has a known mass, the peak of the velocity versus time graph can be used with the mass to determine the maximum kinetic energy of the cart. That, of course, would be 1/2 mv squared. And so if you just go to the velocity versus time graph, you can see here this velocity versus time graph, at least to me, very obviously peaks out at 0.5 meter per second, right? This is positive 0.5 meters per second. So we very clearly know what the maximum speed of the cart is, and therefore, if we knew the mass, we'd very easily be able to figure out the maximum kinetic energy of the cart. That, of course, could be used to determine the maximum elastic potential energy of the cart, since the mechanical energy is conserved. So as I said here, since the mechanical energy is conserved, the maximum kinetic energy is equal to the maximum elastic potential energy. And if the spring constant is known, the equation 1/2 Ka squared is equal to the elastic potential energy maximum can be used to solve for A, the amplitude. Now, that answer is a little sketchy because it sort of relies on a lot of things being known that you may not necessarily know. And so I was thinking about it, like, well, what else could you possibly do if you didn't actually know the mass and you didn't actually know the spring constant? And I was staring at that velocity versus time graph and staring at it and then realized, oh, it's a velocity versus time graph. The maximum compression of the spring is a displacement. And so the second possible answer here is, since this is a velocity versus time graph, the area under the curve can be used for a quarter cycle of the graph. This is actually something that's really important to know for the simple harmonic motion problems anyway, since you will see this phrasing, a quarter cycle of the graph, in multiple choice section answers. And so it says here, as I wrote in parentheses, the section from the maximum velocity to the point of zero velocity. It doesn't really matter which way you go, from maximum to zero or zero to maximum, since the area under the curve is equal to the displacement for a velocity versus time graph. Now, here's the deal. If you start, let's say here at 2.5 seconds, the object is moving with a velocity of 0 meters per second. That means it's at the amplitude. So we can say right here, this point corresponds to x being equal to a, the amplitude. When it gets here, that's where it's at the equilibrium position, where x is equal to 0 meters, or at the equilibrium position. So when we say a quarter cycle, we mean the area under the curve from the 0 to the peak. And so that would be this section here that's shaded in. Notice you can estimate that by finding the area of that triangle. Now, of course, that's going to be not a great estimate because the graph is curved, but you get the idea. That area under the curve that I have colored in here is going to be equal to the amplitude. The area under the curve is going to be equal to the amplitude. Now, the reason why you don't use the whole positive section of the graph is because this is a velocity versus time graph, and the area under the curve is giving you the displacement. And it's important to realize, if we are saying the object is starting at the equilibrium position and then moving back to the amplitude, it's still in this positive displacement territory when the object is moving to the amplitude and then back to the equilibrium position from the amplitude. And that's a key thing to recognize. If you do it over this entire half cycle, notice here the velocity is 0, so the object is at the amplitude. It moves to the equilibrium position and then back to the other amplitude. And so notice the velocity is always negative, so that means it's moving in the same direction, but it's basically traveling double the amplitude. And that's the important thing to realize here. You can only get the area under the curve equal to the amplitude if you take it for 1/4 of the period, because in an entire period, the object goes from the amplitude to the equilibrium position, so that's the amplitude, another distance equal to the amplitude when it goes from the equilibrium position to the other amplitude, back to the equilibrium position, and then back again to the starting point. So in a whole period, it travels a distance equal to 4 times the amplitude, right? An A from the amplitude to the equilibrium position, another one from the equilibrium position to the amplitude on the other side of the equilibrium position, back, and then back again for A. That's why they are always going to say in these kinds of questions, a quarter cycle. Now, this point is very important. So I'd like everybody to take a second to pause this video here and write this down. And when you hit play, we'll move on. All right, so if we look at the scoring guide here, notice the scoring guide allows you to say both of those things. You get 2 points for this, and you could say 1 point for indicating that the area under the curve somewhere is needed. And then the second point is specified for knowing exactly which portion of the graph you need to find the area underneath to get the amplitude. The second version, like the alternate response, if you will, is for indicating that energy is conserved, and that if you take the maximum velocity, you can take the maximum kinetic energy equal to the maximum spring potential energy and solve for it that way. Now notice it doesn't say anything here about knowing the mass and knowing the spring constant, but the point still stands. Your example responses can be take the area under the curve for 1/4 of a period, or energy is conserved during the oscillation, and therefore energy at the equilibrium is equal to spring potential energy at the extremes. By setting those two values equal to each other and using the max velocity from the graph, we can solve for the maximum distance and determine the maximum distance the spring is compressed. Of course, notice they said nothing actually about knowing the mass of the cart, but they at least mentioned the spring constant K at one point. And you could use the graph if you wanted to find the period, and then use that period, if you knew the spring constant, to find the mass that way. There are a lot of ways that you could go about accomplishing this here. And that's an important thing to realize, the connections between all these little tricks and tips for the simple harmonic motion unit. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to part D. All right, now part D of this question says the plate of negligible mass is replaced with a plate with mass similar to the cart's mass, and the collision is repeated. Then it says here, again, the cart moves with a velocity v cart. And so it collides with and sticks to the plate and oscillates back and forth. The question now says, in a clear, coherent, paragraph-length response, explain how a graph of the cart's velocity as a function of time would differ from the one shown above if the plate's mass were not negligible. provide a physical reason why each difference would occur. Now, it's important to realize this velocity versus time graph is not showing you a whole lot. In fact, it's really only showing you two things. It's showing you the maximum velocity that this thing experiences, or at least the maximum speed, right? The maximum velocity is plus or minus because the thing changes direction. And it shows you, if you're taking the time between, each cycle, it's showing you the period. Now, as it turns out, both of those things are going to change. And they're going to change for very good reasons. And hopefully, the simulator activity from the other day sort of helped you to realize that a little bit. So my answer to this one is a little long, but there's a lot of detail that needs to be given in this answer. This is a 6-point question. So the first thing I wrote here is, if the plate was replaced with a plate with a larger mass, the oscillating system would oscillate with a larger mass. Since the period of the oscillation is dependent on the mass of the system, the period would be different. That's just a fact. Now, I decided to talk about period first here because I thought we could just knock that out, talk about the equation, sort of one contained idea. It's a pretty easy thing to just mention first. So as I said here, since the period of a system oscillating on the spring is directly proportional to the square root of the mass, according to the equation, the period is 2 pi times the square root of m over k, the larger mass of the system means the system has a larger period. That's it for the period part of it. And since that's really half of the detail you can get from the graph, that's going to be worth a pretty decent chunk of the points here. And so now that we've addressed the period part of the graph, we have to address the amplitude part of the graph. And hopefully you realize from the simulator activity the other day that the amplitude has something to do with the energy here. And so we're really going to need to take a good hard look at the energy for the whole system. So as I wrote here after that, black vertical line, since the plate now has a non-negligible mass, the cart's collision with the plate must be considered a perfectly inelastic collision, which means the cart will lose kinetic energy in the form of heat. Since the system will be oscillating with less kinetic energy, the maximum velocity of the system will be less, since the total energy is less, which means the graph's amplitude will be less. So that's an important thing to realize here. The fact that now instead of the cart crashing into a plate that basically has no mass, it's crashing into a plate that has some significant amount of mass, almost equal to the mass of the cart itself, that's a perfectly inelastic collision because they stick. And because it's a perfectly inelastic collision, there's energy lost. And so in this particular situation, now that the cart is moving along with, I think as they say in the problem, V cart, and then crashes into the plate, there's automatically going to be less energy in the system. That means the maximum velocity of the system is going to be less. And so the graph's amplitude here, which shows the maximum velocity, which, as I mentioned in this graph, is 0.5 meters per second, that's going to be a smaller number. And so there's how you get there from your energy analysis. Since the total energy is less, when the kinetic energy is converted to elastic potential energy, the elastic potential energy will be less. And so the amplitude of the oscillation is going to be less. That's the basic detail here. There's a lot here. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so looking at the scoring guide here, again, this question was worth 6 points. It's a paragraph length response. And so, of course, that last point here is going to be for just writing the paragraph and being logical and coherent. You can see here the first point is for recognizing the period is going to be a different number. Now, notice here it says not necessarily longer. If you just said the period is going to change, you get that point. The second point is for indicating that the period is going to be longer, and that's because there's more mass. You get 1 point for recognizing that there's going to be kinetic energy loss because this is an inelastic collision, and therefore there's going to be kinetic energy converted to heat. You get 1 point for stating that the amplitude of the graph will be different. And they say here, notice not necessarily less. And then you get 1 point for indicating that the amplitude is going to be less because the system has less energy. Notice there, you could have also said the amplitude will be less because a greater mass means a smaller velocity because of conservation of momentum. But I think that really seems kind of odd to go through this whole energy analysis and then say that at the end. So notice here, they said, with an additional mass due to the plate, the period would be longer since the period increases with mass. Some of the initial kinetic energy of the cart will be dissipated in the completely inelastic collision with the plate if the plate has a non-zero mass, so there'll be less kinetic energy immediately after the collision. With less kinetic energy at zero spring displacement, there is less total mechanical energy that be converted to spring potential energy. So the maximum spring potential energy will be less, and therefore the amplitude will be less as well. Take a second to pause this video here and make sure you really understand all aspects of the scoring guide, and when you hit play, we'll move on. And that's the last part to the first question. Notice here, the bulk of the points was awarded for this last section of this. And even if you didn't get all of the points for this problem, it's important to realize that that's okay. The point of the free response section is to scrape up as many points as you can. That, of course, brings us to the second question. Now, this is not the last time you're going to see this setup, because they actually made a bunch of different versions of this question for last year's AP exam. It was the same, track here shown with this curved ramp, but there were a lot of different versions of it. And I actually like a number of them. So we're going to continue to hammer this home, because I think this setup actually is a pretty good way to be able to mix a lot of different topics. And so keep in mind, even if you had a rough time with this one, you have not seen the last of this kind of setup, and this is going to be important for the future. So looking here at the question, it says two discs A and B are initially at rest on the left end of a track as shown above. Disc B is more massive than disc A, which they kind of show you because they make it a lot bigger. The track has a horizontal section and then curves upward at the right end. The discs are each pushed to the right over a distance x naught by identical constant horizontal forces of magnitude F. There's negligible friction between the track and the discs. Part A of this question here says, which of the graphs shown above correctly models the velocity of disk A as a function of the position as it's being pushed by the force? Justify your answer. Now, I'll be perfectly honest. When I looked at this question and didn't really read it carefully, I was just like, oh gosh, this is so easy here. It's asking you about the velocity versus time graph for a constant force. And a constant force is going to produce a constant acceleration, so it's going to be graph 2. Of course, some of you, if you're paying attention to the words I'm using, might have already caught it here. This is not a velocity versus time graph. This is a velocity versus position graph. And so while I don't think this question is impossible, it's a little harder than I might have originally anticipated. Really, what you have to do here is look at an equation which gives you a relationship between the velocity and the position. There are actually a few ways to do that. To me, when they said here at the very beginning, force and displacement, the first thing that I'm thinking of is work, right? Because work is the product of force and displacement. And notice I didn't write the cosine theta part here, because very clearly from this image, the force is parallel to the displacement. And what you need to realize in this particular example is, and really in all examples, is that the work is equal to the change in total energy. And in this particular example, that means the work is equal to the change in kinetic energy. And so the work here, the force times the displacement, is going to be equal to the change in kinetic energy, which notice here, since they say the disk is initially at rest, it's just going to be equal to the final kinetic energy. Now, this equation is actually going to prove itself to be very important, because it gives us a nice relationship, really, between everything we said about forces and everything that we could say about energy. This really is the bridge between a dynamics analysis and an energy analysis. And of course, if you look at this equation here and you solve it for the velocity, you get 2 times the force, and here there's no subscript, times the displacement, and then divide that by the mass, of course, all under the radical. And so that equation shows you the final velocity is not directly proportional to the position. The final velocity is directly proportional to the square root of the position. And so your answer here should look a little something like this. Graph 1 correctly models the velocity of disk A as a function of the position as it's being pushed by the force. The work done on the disk is equal to the disk's change in kinetic energy. The work done is given by the equation work equals force times displacement, and the kinetic energy is given by the equation, of course, K equals 1/2 mv squared. So the work done is proportional to the displacement, and the kinetic energy is proportional to the square of the velocity. Since the initial kinetic energy is equal to 0, the work done on the disk is equal to the final kinetic energy of the disk. This means the relation F delta x equals 1/2 mv final squared can be solved for the final velocity as V final equals the square root of 2f delta x over m. Now here's the big part here. This equation shows us that the puck's final velocity is directly proportional to the square root of the distance. That's really important. And because the final velocity is directly proportional to the square root of the distance, it's going to look like a y equals square root of x graph. Now, if you are not familiar, I'm going to come back to this and let you write it down if you want to, but if you're not familiar with what a y equals the square root of x graph looks like, all you have to do is look at your calculator. If you look at your calculator and you go to the y equals part and you put in y equals the square root of x and hit graph, then you'll be able to see in the first quadrant, it looks like graph 1. It's sort of like this curve up that eventually levels out. That's what a graph of y equals the square root of x looks like. Of course, if they were not proportional by this square root business here and just directly proportional, you all know what that's going to look like. It's going to be a straight line. That's what graph 2 was. So the very fact that you know they're not directly proportional means you know the graph is not going to be a straight line. Now, take a second to pause this video here and write this down because this is very important. Make sure you're adding any parts of this explanation that may be missing from your own. And when you hit play, we'll take a look at the scoring guide. All right, looking at the scoring guide here, this one was worth 3 points. It says here, note at the very beginning, indicating the velocity is proportional to the square root of distance or position earns both the second and third point. So I really kind of overly explained in my explanation because notice, look at what the second and third point is. It says 1 point is earned for indicating that the work done on the disk A is proportional to the position, and then 1 point for an explanation that includes that the velocity is proportional to the square root of the work. Now, I first looked at this and didn't see that note above and thought, well, that's stupid. Why would you explain it in that sort of drawn out way when you could just say, hey, look at the equation. The final velocity is directly proportional to the square root of the position, period, end of story. They give you that here. And so that's an important thing to realize. So you get 1 point for the answer, that it's graph 1, with some attempt at a justification, and then 2 points for that explanation. Now notice here, I think that this would be important to point out, you could also earn the point for indicating an appropriate kinematics relation between velocity and position, and for an explanation that includes that the velocity is proportional to the square root of the distance or the position. If you chose, and this I often encourage you not to do, but if you're talking about kinematics and an energy problem, Vf squared equals V naught squared plus 2a delta x, when an object is at rest, it is absolutely the case that the final velocity is equal to 2a delta x, meaning the final velocity is directly proportional to the square root of x, which would give you the exact same answer. So either way you say that one, it works. Having said that, if you're looking at a question on the AP exam and you're seeing a force is being used to push an object for a distance and you're not thinking about work, that may lead to some issues. So thinking about work, thinking about energy is a really important thing in these problems if they're talking about force and displacement. Of course, if they're talking about force and time, then you should be thinking about impulse and momentum. But force and displacement, key highlight for work. Take a second to pause this video here. Make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to part B. Now, some of you might have gotten suckered in with this question into choosing graph 2 because we usually see straight lines on velocity versus time graphs. Of course, the only problem with that was the x-axis variable wasn't time. So I'd like you to write down this note before we take a look at part B. This note here says to determine the shape of a graph, you must always look at the equation that relates to two variables. Specifically, you should solve the equation for the variable on the y-axis and use the equation to determine the relationship with the variable on the x-axis. This is going to be an invaluable piece of knowledge for the test. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, and that brings us to part B of this question here. Part B of this question says, after sliding across the horizontal portion of the track, both discs slide partway up to the curved section of the track. Identify which disc, if either, reaches a greater maximum height. If both discs reach the same maximum height, state this explicitly. Now, again, and I'm quite sure I mentioned this when we were talking about the last question today, and other times during our review. You got to pay really close attention to what they are asking you in the question and how they are asking it. Notice it does not say identify and explain. It says identify, state. You do not need to explain for this one. The answer here is going to look like this. Disk A reaches a larger maximum height than disk B, period, end of story. Disk A has less mass, that's true, and you can go through the whole thing, but they do not want you to do that for this part. We're jumping straight to the scoring guide because this one is easy. 1 point is earned for the correct identification of disk A. Done. Now, you could have probably literally just written disk A and they would have given you the point. Now, I think you should always write at least a sentence because, you're almost in college. But disk A will go higher on the track as their example response. Perfectly reasonable answer. Now, of course, if the question is, why shouldn't you be wasting your time at all doing an explanation for this part? It's because what they're asking you for in part C. Part C says in a clear, coherent paragraph length response, justify your answer for part B. So now in this part, we're tasked with explaining why disk A is going to reach a higher height than disk B. And I hope everybody realized if they're asking you a question about which object is going to reach a larger maximum height, you're thinking about energy. It's a ramp and they're asking you about height and you're not talking about energy. That's bad. So for this one, there's a lot of things you could have said. I mentioned this already in this question. Thinking about this question in terms of work is just going to make your life so much easier. And so for this one, I wrote, both disks start their motion with zero energy and have the same amount of work done on them. That's a fact. They have a force of the same size being exerted on them for the same displacement. They're going to have the same amount of work done on them. That means their energy is going to increase by the same amount. So I wrote here, when the force stops acting, both pucks will have the same kinetic energy. And when they get to their maximum height, they'll both have the same gravitational potential energy, as the energy in the system is conserved. They start with no energy. That force does work and gives them energy. Because it's the same amount of work, it's the same amount of energy. That's really the point here. And so, yeah, that energy is going to change form. The force is going to accelerate the objects, turn that energy into kinetic energy. The object is going to move up the ramp there. That energy is going to turn into gravitational potential energy. But the whole time, it's going to be the same. And that's the key detail. That brings us up to here in the explanation, up to the word conserved. After that, I said, however, this is the part where we're differentiating the motions. However, since the objects have different masses, they will have a different maximum speed, even though their kinetic energies are the same, and a different maximum height, even though their gravitational potential energies are the same. Since the gravitational potential energy is given by the equation U equals mg delta y, the object with the smaller mass will reach a larger maximum height in order for the gravitational potential energy to be the same. We've done like a good amount of questions about this already, and almost all of them want you to compare the energy and then compare the quantity associated with that type of energy. It is 100% a fact. Both of these objects have the same gravitational potential energy. And what is a fairly big misconception in physics is people think if the equation says the gravitational potential energy is directly proportional to the height, which it does, then the fact that they have the same gravitational potential energy means they have the same height. Some of you who are about to listen to me say this have probably heard me say this before. You have to be careful by making generalizations about relationships in equations, because we often say gravitational potential energy is directly proportional to height. But you got to remember, you can only say that from this equation, UG equals mg delta y, if the other things in the equation are the same. If the masses are the same and if g's are the same, then the object with a higher height will have a higher gravitational potential energy. But the gravitational potential energy is also dependent on the mass. So the point that I'm trying to make here is, even though the objects have the same gravitational potential energy, which they do, that doesn't necessarily mean they have the same height. And the reason why they don't have the same height is because they have different masses. The product of m and delta y has to be the same for both of them. So that means the one with the smaller mass is going to have a larger maximum height. And that ultimately is why A is going to reach a larger height. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the scoring guide. All right, taking a look at the scoring guide here. The scoring guide says this part of the question was worth 5 points. Notice that last point is for the paragraph length response format here. So you got 1 point for explaining both of the disks have the same amount of work done on them, or you could have said they have the same force but different masses, so the smaller mass is going to have a greater velocity. That works too. Same force, different mass, different acceleration. Of course, different acceleration means different velocity. That works. In my opinion, you'd be insane to not talk about the work. They're setting you up by talking about force and displacement. You get 1 point for talking about conservation of energy. That's a home run on this one. It's a freaking ramp and a block, and they're asking you about the maximum height. You're not talking about conservation of energy, you're nuts. 1 point for indicating both disks have the same amount of gravitational potential energy at the maximum height. That one's not obvious, but eventually as you do more and more of these questions, you realize that's what they're setting you up for. A lot of kids might think they have a different height, so they're going to have a different gravitational potential energy, or if they have the same height, they'd have the same gravitational potential energy. That is not the case. They have the same gravitational potential energy. They have different masses, so they have different heights. And of course, that's what the last point is for indicating that a larger mass will reach a smaller height, or vice versa. And they gave you an alternate response for that one, which was for indicating that a disk with a higher velocity will travel to a greater height. I think it's perfectly reasonable to say that. I don't know that that's the easier way to explain that, but of course, that could get you some points as well. Take a second to pause this video here and make sure you understand all aspects of that scoring guide. And when you hit play, we'll move on to the final part. All right, moving on to part D here. Part D says, consider the case where friction is not negligible and the coefficient of kinetic friction between each disk and the track is the same. The disks are again pushed by the same force over the same distance, and each disk slides partway up the ramp. Identify which disk, if either, would reach a greater maximum height than the other in this case. If both disks reach the same maximum height in this case, state this explicitly. Now, notice here, they're telling you there's the same coefficient of friction. And now we're asked to consider, well, what is the effect of friction? You look in the reference table, you see this equation. The force of friction is equal to the coefficient of friction times the normal force. And of course, because we're talking about kinetic friction here, we can put in the subscript K for the force and the coefficient. And we see here that if the coefficients of friction are the same, which they are, then that means the only difference here with the friction is that the object experiencing the larger normal force will experience a larger force of friction. So the force of friction here is directly proportional to the normal force, which at least on the flat portions of the tracks is equal to the object's weight. Notice again, this comes down to mass. And to me, this was a little bit of a weird one to explain because the lighter disk already reaches a greater maximum height. Now, if we're getting friction in the mix, well, the lighter disk is actually going to experience less friction. So it's still going to make it to the higher max height. And that really is the point. Block A will reach a larger maximum height. The fact that there's now friction means mechanical energy will be converted to heat, leaving behind less energy to be converted to gravitational potential energy. Remember, if you're doing an energy analysis the whole time and now they ask you about friction, pick it up with the energy analysis. Since the friction force is directly proportional to the object's mass, at least when the objects are on a flat surface, block A will experience a smaller friction force than block B, which means it will lose less energy and still reach a larger maximum height, which is also the case when there's no friction. Take a second to pause this video here and write that down, making sure you understand all aspects of this answer here. Make sure you add any parts of this that may be missing from your own. And when you hit play, we'll take a look at the scoring guide for this last part as we wrap it up for today. All right, moving on to the scoring guide here. This one was only worth 1 point, and they gave you 1 point for a correct justification. Here it says, without friction, disk A goes higher. With friction, disk B experiences more friction. So disk A will still go higher. Again, my answer was a bit extra, but that's the idea. B experiences a bigger frictional force because it has more mass. And so it's just going to lose more energy. And if it loses more energy, it's just not going to go as high. That's the basic idea. Now, of course, you can realize if you're looking at the question, you don't need to go too nuts about the explanation here, because notice it says, briefly justify your answer. And if you're briefly justifying your answer here, you don't need to go nuts with this overly detailed explanation. Quick little 1 or 2 sentences does the job. With that, that's it for today. There is only one free response question assigned today because you have some simple harmonic motion homework to check over and do. And of course, this video to watch reviewing the free response questions from yesterday. So with that, that's it for today. And tomorrow, the video will be about the free response question you were assigned today. All right, everybody. Have a good one.